Let me start the recording. Okay, so today we don't have a lot. We just have 20 slides and we'll go over them pretty quick. Okay, so today we're going to talk about chapter 1, part 2, which both of you did the quiz already. So I assume that you know all of this stuff because both of you got 100 on it. Okay, let's start.
Time myself. I'm trying out for my little girl. She was fine. Give me 1 second.
Yeah,
Okay.
good, you're good.
Get out. Get out. Get out. Get out. Get out. All right. I'm done.
You good? All right.
Yeah.
Okay, we finished on hardware. The last video that I recorded finished on hardware, so now we're just going to talk about software a little bit. Yeah, everything that you see on your screens is controlled by software, and it's written by coders. It's basically what we're trying to get you to start doing is writing software. And there are two types of it. There's system software and there's application software. You will probably Personally, I've never in my life met someone who was working on system software because 99% of the industry is just application software. And let's see. Okay. What is system software? System software is basically like Windows, Linux, Mac OS. It's your operating systems, okay? It's what's built into your device that you're using. That you cannot download system software because it's already downloaded on your device that you're using. Like on your iPhone, whenever you get an update, like update your system, that's operating system software. Okay. Same with your laptop. Same with your watch. Whatever. Everything has an operating system. Application software, yeah, 95% of all software is application software. It's the programs that people spend most of their time on. It's like social media, it's your Word, PowerPoint, Google Docs, whatever. Everything that you can download on your iPhone or on your phone, on your laptop is application software. All right, let's move on to how computers store data. Dee, you might be familiar with this information. I'm not sure if Nicole, if you are, but we'll just go over it again. So everything that you see on the screen is made of zeros and ones. And I know it's crazy to think about that. It was crazy for me to think about that, but literally every single thing that you see is just zeros and ones at the end of the day. And how that happens is actually, no, I'm not going to talk about it right now. We'll talk about it later. There's a couple of slides on it. So computer's memory, everything is stored in a tiny storage location known as bytes, and bytes are divided into bits. So how it goes, bits, the smallest one, bytes, a little bit larger than bits. 1 byte will represent one number, and 1 byte consists of 8 bits. You can see it over here. So this is how I want you to imagine a byte, okay? There's like we have 8 switches, 8 on and off switches right here. This is one memory location in your computer. So, and each of these things is a bit. All right, this is a bit, this is a bit. And yeah, bits are just, as it says, tiny electrical components and can either hold a positive or a negative charge, which means it can either be 1 or 0. If it's a 1, it means the switch is turned on. If it's a 0, the switch is turned off. So this is a 0 and this is a 1. It will all make sense. It'll make sense in a little bit, I promise. What happened there? Clear? All right. Okay. Yeah, this is a little bit a visual representation. So as I said, 1 represents a true, 0 represents a false. And that's one of the things that you just got to remember. It might not make sense to you, but if you remember it, the more you use it, the more it will make sense. So 1 is true, 0 is false, and this system is called the binary because by 2, the binary. What we're using right now, just as humanity, we're using the decimal system, which 10. So this is binary 2. And each position in a number, you see, this is the same thing. Like imagine these are switches, okay? So this is your one switch, this is your other switch. These are all switches. This switch is turned on, this one, and this switch is turned off. And every single position has an assigned number to it. So the 0 position in an 8-bit number is 2 to the power of 0. The second one 2 to the power of 1, and so on and so on. Okay. Let's see. Let's actually figure out what the number is, right? Like what does this number mean? So what you need to do if you're trying to figure out a binary number and translate it to the decimal, to what we use as humans, all you need to do is, if you see a 1, figure out which position that 1 is standing in and just multiply it by that power of 2. So we have 1 0 0 1 1 1 0 1. What we're gonna do, if my computer will start, thank you. All right, so this position right here is 2 to the power of 0. So what you need to do is just, if you see a 1, all you do is you take 1 multiplied by 2 to the power of 0. Then the next one, we see a 0, but we know that this position is 2 to the power of 1, but since it's a 0, we can either just disregard it, or we can do 0 multiplied by 2 to the power of 1. And moving on with the same thing, plus 1 multiplied, and we know that this position is 2 to the power of 2, 2 to the power of 2, and so on and so on. And you see what they did? They didn't really explain it here in this picture, but they essentially did the same thing. So we have 1, it's right here, 1. Then they skipped 1, because if you multiply by 0, you get 0. Then they went to the next one, is 1 multiplied by 2 to the power of 2, right here, 4. Then they went to the next one, is 1 multiplied by 2 to the power of 3, which is 8. And same thing, 1 multiplied by 2 to the power of 4, 16. And then skip 1, because when you see a 0, just skip it, and then 1 to the power of 1 multiplied by 2 to the power of 7, 128. See, same thing with the switches right here. They just show it with the switches. So this number right here in the binary system translates to the 157 in decimal system and what we use. Does that make sense? No?
No.
No?
Why we skipping 0?
We are skipping 0 because remember I told you that 0 means false and on the other slides?
Oh,
Let me see. We'll go back.
right.
Yeah. So how previous?
No, I remember you saying it's false.
Huh?
Okay.
And 1 is true.
Yeah. Just think of it as 1, the switch is on, 0, the switch is off. Okay? And if the switch is off,
Right.
we are not gonna get anything from that switch basically because it's off, it's not working. And the switch is working. Make sense? Okay.
Yeah, I get it.
It's gonna make sense the more you do it, the more, honestly speaking, I've never used the binary system outside of the classroom and translating the numbers outside of the classroom, but it's important to know. It's just important to, because it's the basics and it's the standard, and this is what the people in the industry are using every single day, so we just gotta know this stuff. So the largest value that can be stored in 8 bits or a byte system is 255. And how do we know that? If we turn all of the switches on, if they're on and on, every single switch is a position on, then we just add all of the powers of 2, right? Because we know that this position right here is 2 to the power of 0. This is 2 to the power of 1. This is 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 5, 2 to the power of 6, and 2 to the power of 7. If we multiply 1 to each of these, 1 multiplied by 2 to the power of 0, 1 multiplied 2 to the power of 1, and then we add all of those things, this is what we're gonna end up with. And this number is going to be 255. Okay, 128 plus 64 plus 32 plus 16. So the largest value that you can store in 1 byte is 255 in the system that we use in decimal. And then you can use as many bytes as you want. You can get as big number as you want. I don't know, but for some reason they decided to give you an example of 2 bytes, and the maximum value is 65,535. All right, let's move on. What do we have? All right, storing characters. That's an interesting topic. I like this topic a lot. So characters are also stored as binary numbers because everything that you see on your computer is stored in zeros and ones. So people had to figure out which number will correlate to which character, right? Because we can't just if we just have the numbers or integers, what's that gonna do? We can't communicate with each other using just numbers, all right? Like we need letters. So
Right.
yeah, so characters are also stored as binary numbers, and there are two main systems that people use. It's either ASCII, American Standard Code for Information Interchange, or a Unicode. Unicode is more full. It works with ASCII, but Unicode can also be translated to many different languages, and ASCII can only store 128 characters. And I have a table to show you the ASCII table. Okay, so this is the letter A. Wait, actually, I'll show you this table first. So as you can see here, 128 characters, because we start from 0 here. We start from 0 and we end at 127, so it's 128 characters that we have here. And you can see that disregard the hex table, just look at the decimal and the character table. So as you can see, number 65 in decimal is translated to a character A, number 66 B, and so on and so on. With other, like 36 will be a $sign. It's just somebody came up with it. It's not like it was made this way. Like somebody came up with the system and people were just like, oh, that sounds cool, we can use it. Right? Yeah. Same thing like the binary system. Somebody just came up with it and now we're all using it. All you need to know about the ASCII table is that you can Google it. It's really easy to find it. If at any point you will have to find out what a character is in ASCII, like how your name is spelled in ASCII or something like that, you can easily find it on the internet. You just need to know what to look for. You just Google ASCII character A decimal or ASCII character Q decimal, and you're gonna get a number. Unicode, same thing, just more extended list. It uses more decimals. It uses 2 bytes of as I showed you before, 2 bytes of in binary. Wait, I'll go back to that. Clear. See, 2 bytes. So if we use 1 byte, it's only 255 characters that we can have. If we are using 2 bytes, it's 65,000. Oh my god, 65,000. So that's why Unicode is more extensive, just because it uses more. It has more storage. All right, let's move on. All right, any questions about how we store data before we move on to the next?
No.
We're good? Okay. We sure? All right. Now we're moving on to figure out how a program works, or how to start writing our first program. Computer CPU can only understand, as we spoke about CPU is basically, think of it as a brain of the computer. It can only understand instructions that are written in machine language, and machine language is zeros and ones. Okay, this is what we call machine language, because people find it's really difficult to write programs just in the machine language. Because imagine writing thousands on thousands of zeros and ones, and if you mess up one of the zeros or one of the ones, your program crashes. That would be crazy. That would be crazy to write. That would take hours, days, weeks to write just one simple line of code. So that's why people came up with programming languages such as Java, Python, C++, C Sharp, name it. Programming language were just created to help people write machine language code. All right. So this is what your CPU can do. It can read a piece of data. It can add two numbers. It can subtract a number from another number. It can multiply two numbers. It can divide a number by another number and move a piece of that data from one memory location to another and determine whether a value is equal to the other value. So CPU is not that smart. It's not that smart as we think it is. The smart part comes from the programmers, comes from the coders who give the instructions to the CPU, basically. Yeah, so CPU can only understand instructions written in machine language, only zeros and ones, but yeah, all right, we don't need all that. So this is how it happens. So fetch decode executes cycle. This is how the CPU reads the instructions that you give to it. So it gets, it fetches the next instruction in the program. It finds what you would like it to do next, okay? Then it decodes it, it reads the zeros and ones, and it figures out what those zeros and ones mean, and then it executes the instruction, and then it moves forward. So it grabs the next instruction, next number, it figures out what that number is, and it executes that instruction. And that's all it does on end. This is just this happens in microseconds, okay? Now, how do we get to the machine language from our Java, from our Python? How do we get to that place, right? How do we get to zeros and ones? Assembly language comes into place. Assembly language was created to make writing the zeros and ones easier. It's considered a low-level language, and it just uses short words that are called mnemonics to help the developers translate what they want to do into zeros and ones. What it looks like right here, and nobody really uses assembly language anymore, but if you really learn how to do it, you will get a lot of money because nobody wants to do it because it's really hard. So if you really learn assembly language, that's what I was told when I was in school, that if you get really good at assembly language programming, you will have a job for the rest of your life, a career for the rest of your life, because just no one wants to do it, and apparently it's very important in some areas. Yeah, so this is what happens. Basically, like move let's see, like move EAX is just like a variable names. Think of it as just any name that, like X, Y, Z, it doesn't matter. So move something to the location Z, then add something, add 2 to that variable, and then move a different variable to the location where our first variable was. Either way, it doesn't really matter. But we lost one. We lost one. Maybe she'll be back. Yeah, it's just words. So you use a word, and then the assembler will translate it into zeros and ones. It's really it's still really difficult. We had to write a program. We had to write 2 programs in assembly language, and it took me hours just because the way the assembly language programming like makes you think, it makes you think like a computer, and it's very difficult to switch your mind, because for me personally, like thinking logically as a computer is hard, because I tend to not guess, but I don't know how to explain it. Like I tend to think forward, like this couple of steps forward, what I'm gonna do next, if that makes sense. Like I think like, okay, I'm gonna do this, but then after that, this is what I'm gonna do. And computer does not think that way. Computer does not care what you are thinking that you're gonna do after. The Computer only sees one instruction and that's it. It doesn't care what you did before, it doesn't care what you're doing after, just one instructions that's in front of it. That's it. All right. Yes, so what's important to know from here is that any code that you write, it can also be called a source code. If someone tells you, show me your source code, they just want to see what you've written. It's not some special code. It's just your lines of code. Yeah, and then source code is translated to machine language using a compiler or an interpreter. With Java, it's a compiler. With Python, it's a compiler. With some other languages, it can be an interpreter. And the difference between the two is let's see, yeah. So a compiler is a compiler translates a high-level language into the separate machine language program, which we can see right here. If we want to print hello Earthling, who would write that? Anyways, print hello Earthling. The compiler would do your work for you and translate it into zeros and ones, and then send it to the CPU. And then the CPU does, fetch the code, execute. That's literally what it does. It's gonna take the first number. Decide what it means, and execute whatever instruction that is. When it comes to interpreter, so it translates and executes the instructions at the same time. So interpreter is basically it executes the instructions for the CPU. It tells the CPU what to do. Basically, that's the difference. Compiler lets the CPU decide what it's doing, and the interpreter tells the CPU, this is what you're doing.
Okay.
Yeah. Oh, this is all I had for today. Interesting. Okay. Do you have any questions for me?
No.
All right. Tomorrow.
At least not today.
Tomorrow I'm gonna post a video about chapter 2,
Okay.
one half of chapter 2, and there's gonna be another question just for attendance on there. And on Thursday you're gonna have a quiz is gonna be posted at 8 a.m. the same way as today it was posted on chapter 2. And I will try to post a couple of labs for you to do. I just need to not translate them, but like make them fit into Google Classroom. And I'm still trying to figure out how to do that, how to put a lab into Google Classroom. But yeah, I will do that. And then starting next week, what I'm gonna do, I'll try to post everything, all of the material for the week. So if you want to go ahead, like go faster than we do, you will be able to do so. Okay, but yeah, just give me some time. I'll do it over the weekend. Yeah.
Okay, well that sounds good. If I have any questions about like software development or whatever, I'll reach out to you because I know you say you have some friends who do that.
Absolutely. Yeah. Let me know. Shoot me an email. I prefer email, but if it's something that's you really need to know like right now, just send me a text. But if I can't wait, yeah, shoot me an email.
Okay, sounds good.
All right, have a good rest of your day, and I'll see you Thursday, 6 p.m.
Okay, alrighty.
Bye.